Hello world. Hello everyone. Good morning, good afternoon, good evening, depending on your location. Welcome to this 8th session of the 6G Research Visions webinar series. I am Nurul Huda Mahmood from 6G Flagship, University of Oulu, and I have the honor of moderating today's webinar. As you know, 6G Flagship has recently published a series of white papers detailing different aspects of what 6G will be. Today's webinar will be a deep dive into one of these white papers titled Critical and Massive Machine Type Communications Towards 6G. We will open today's webinar with some opening remarks from Professor Matti Latva-Aho, who is the director of 6G Flagship. After that, we will hear from our distinguished panelists, Professor Petar Popovski, Mr. Frank Burkhardt, Professor Ingrid Moerman, Professor Christian Wietfeld, and Mr. Ravikumar Pragada. A few practicalities before we begin. We recommend that you use your full name in your Zoom profile. At least half an hour will be dedicated after the presentations for Q&A session. You may write your short questions to the Q&A window at any time during the presentation, either using your full name or anonymously. If you want to indicate your question to a specific panelist, please specify the panelist's name in the question. For your information, the webinar will be recorded, including the Q&A session, and the video will be openly available on the event website after a few days. In order to promote wider discussion, please use the following hashtags when discussing the 6G white papers and this webinar on social media. Without further ado, I would like to give the floor to Professor Matti Latva-Aho for his welcome message. Matti, the floor is yours.
Thank you, Nurul, and hello, everybody. As we all know, 5G is the beginning of a new era towards intelligent, wirelessly connected world, where all sorts of processes, machines are connected wirelessly to internet. They are also able to communicate between each other for the benefit of us all human users, so that our lives become smoother, easier, faster, more enjoyable, all in all. 5G is just the beginning, and since this set of requirements that machine type communications have set to mobile communication systems design, we all understand very well that this is not going to be the end of the story. On the contrary, we need to continue our research efforts, and eventually industry has to make sure that it goes to implementation phase, how to make these machine-driven communications as smooth, as efficient, as fast, whatever we are requiring from it as possible. So we need to keep working really hard to take it further in the standardization work, and also beyond that, I think it in many cases goes beyond our imagination. So this particular white paper is something that really inspires me a lot, and there are a huge number of very interesting research questions which will keep us all very busy. And the subsequent speakers are going to give you an idea about what the research challenges in this particular area are now and for years to come. So I welcome you all to this webinar, and I hope you enjoy all the presentations, and please set interesting questions as well from the audience to all speakers. Thank you and enjoy the webinar.
Thank you, Matti. So as we have stated, today's webinar discusses the white paper on critical and massive machine type communications towards 6G. This white paper is authored by 31 experts from 15 different organizations spanning across the globe. It has 6 main sections covering the key drivers and requirements of MTC and emerging MTC-specific service classes, holistic MTC network architecture, energy-efficient MTC devices, massively scalable MTC, mission-critical MTC, and last but not least, privacy and security for MTC. Due to time limitations, we will not be able to cover all of these topics in this webinar. However, the complete white paper, along with other white papers, are available for download from 6gchannel.com. Let us move forward to the first presentation of this webinar, titled Key Requirements of an MTC-optimized 6G Network. The presentation will be given by Professor Petar Popovski from Aalborg University, Denmark. Petar, the floor is yours.
Okay, so so I'm going to talk about some key requirements of the MTC-optimized 6G networks, or as I would prefer to say is post 5G, because that's the only thing that we know, that something will come post 5G, but will be the G in the same sense as it was before. We're not really sure. And I'm going to cover a couple of topics within the next 10 minutes. First is the types of connectivity that we are going to see and the challenge of traffic modeling. Second is the performance in terms of timing. Third one is the role of unavoidable machine learning. Fourth one is the spectrum and slicing. And finally, one development which is transforming the type of MTC traffic and the requirements are the trusted interactions and smart contracts, and I'm going to give a brief view on that. So let's start with the connectivity types and traffic modeling. So these are three services in 5G, the broadband, ultra reliable low latency, and massive machine type communication. But I think the main lesson from 5G is that we have to have a platform approach that is flexibly supporting different heterogeneous services. This means that when we thought about which are generic services in 5G, we thought of something which can span the full connectivity landscape. And let's say that this full connectivity landscape is thought to be three-dimensional in 5G, which I'm not sure is correct, but it's a very good start. That means that specific connectivity types will be combination of different types of generic services. For example, in industrial automation, we can have a combination of URLLC and eMBB and some sensor information from MMTC. So the way to think about this is that we're having a population of different connections with different heterogeneous requirements in terms of rate, reliability, number of devices, and so on. And then we are mapping this to three connectivity types, which are our generic connectivity types. So we can think of them as vectors in some connectivity space, as I mentioned before. And then we map them to different interfaces, one of which is prominently 5G, but there could be others, including whatever will be defined as a 6G interface. And so there are at least three cases for long-term ultra-reliable communication, so that we do not rely on the proverbial 1 millisecond latency. So one thing which I think is going to happen is that we are going to redefine the way we are using latency and reliability, maybe not put always just the very stringent condition on 1 millisecond then to the -5, but be a little bit more statistically general in how we're defining these requirements. And for example, the three types of connectivity which would be coping with a larger latency are mobile health, disaster and rescue, and smart grid. For example, in smart grid, many things happen with a cycle of 50 hertz, right, in the European network, or 60 hertz in the other network. So the point is that this cycle is a basic unit of control where some events have to happen, some transmission has to happen, and so on. And if you look into the very good document made by 5G ICA on industrial IoT connectivity, they're actually also going for non-real-time, soft real-time, and hard real-time connectivity requirements in terms of latency, but the reliability can be defined within these periods, right? So basically, the latency reliability space can be generalized beyond what is what has been done in 5G. So in that sense, I suggest that we decouple latency and reliability and actually look at this connectivity space as four-dimensional. If we do that, then, for example, if we have tactile robotics, we have high requirements on reliability, high requirements on latency, which means that the latency is low, data rate not high, massiveness moderate or too low. But then we have health monitors where reliability and massiveness are most important, or augmented reality where latency and data rate are most important, and so on. But from a scientific point of view, I think what we need to have is an improved understanding of the connection ecosystem and how they are interacting between themselves. For example, we are going to see composite connections where we have a low latency traffic arrivals from the same device that are correlated with broadband requests. For example, we have low latency interaction, which is going to be followed by video connection. The question is, how do we make the proper traffic model for this in order to support them in a platform-like system like 5G? Another example is combining massive and ultra-reliable traffic. Let's say that you have sensors which are reporting periodic information about the state of sensing, temperature, or any other, or their battery level and so on. But then from time to time, there's a physical phenomenon, which is an alarm state, and all of them are reporting the same alarm state. So in the first case, when they report massive IoT, they report individual information. In the second case, they report correlated information, which actually means that they act as multiple antennas of the same system, right? Then let's look at the timing performance. So there has been a lot of talk about latency and this machine type communication, but latency is only one of the timing parameters that can be measured. So there is a latency of the radio link, there is end-to-end latency, there is a jitter of the latency, and then there is also the update or age of information. There is also something which is called peak age of information, and so on. The thing is that sticking to the latency and saying just that the latency of the radio link should be 1 millisecond is very limiting. Because, for example, if we have screen-to-screen latency in some video applications, then a lot of the latency budget is actually spent on compression. So the question is, how do we do this form of cross-layered, not very fashionable word these days, optimization of different modules, but we do not sacrifice the good architectural approach. For example, let's say that this 1 millisecond, which was required from 5G, is in some way a victim of architecture, because we want to have a good architecture that relies on reliable connectivity, and we say 1 millisecond would be working for everything well. And let's support 1 millisecond and then build applications on top of it. But having 1 millisecond with very high reliability, it's actually very difficult in all cases. So that's why we have to generalize the latency requirements, and this is something I believe we're going to see in machine type communication. So as I said, latency age, peak age are only instances of the class of time-related criteria for mission fulfillment in the system. Another popular criterion is consecutive errors. So basically, we need to look into this trade-off between good architecture and flexible timing requirements. Third one is the machine learning. I believe I have 3 minutes more. Third one is the machine learning. I think we need to differentiate two general cases for machine learning. One is where machine learning is a must-have, and the other is a nice-to-have. So machine learning is must-have if we want to offer very high reliability guarantees. That can only be done if we have data-driven systems. So if Alice wants to measure and guarantee reliability to Bob, she has to rely on the data in the environment where the wireless system is deployed and provide certain reliability assurances. So if we look into what is the uncertainty in ultra-reliable wireless, we have inherent randomness in wireless because of all the scattering, reflection, and so on. Then we have ignorance about channel statistics, and then we have changes in the channel statistics. So if we want to guarantee certain statistics within some environment, then we have to know to which level of the model we have knowledge of this environment. And that can only be done by using statistical machine learning framework, which consists of 3 elements. One is model selection, next is learning and training, and third one is performance evaluation. And of course, if these systems are deployed in a, let's say, industrial setting, then we need to have continuous learning and adaptation of the models. And nice to have machine learning. This is not to say that this nice to have is just some secondary, non-interesting. Actually, it's very interesting. But what I'm saying is that the solution to complex algorithmic challenges using machine learning and deep learning in terms of resource allocation, distributed learning, multi-antenna optimization, that's nice to have simply because we can do it suboptimally in a different way. But the question is whether we can find really superior ways to solve them using machine learning. Finally, let's look at two more topics. One is the spectrum capacity. I mean, if you look into the call for projects from the EU Commission for beyond 5G smart connectivity, they ask for provision of seemingly infinite spectrum capacity, including innovative spectrum use and management. The thing is that when we are having services with heterogeneous requirements, it's actually hard to define what is a network capacity and let alone achieve an infinite one, which is difficult in any case. So what I'm saying is that if you have one device that wants a very high rate and you have a couple of other intermittently related activity devices that want very high reliability, how are you going to measure the usage of that spectrum by mixing these devices? So we have some proposals on that, but I'm sure that this will be a topic of discussion in the coming years. And finally, one of the topics which I really like is the topic of distributed ledgers, blockchains, and smart contracts, which they are going to contribute to wireless connectivity simply because they are changing the nature of the traffic and the nature of interactions. So that means that if we have massive deployment of IoT devices that are able to execute, monitor, smart contract, and sell or buy data and make interactions with other devices, then the nature of the traffic is going to change. We're not going to have any more uplink oriented only traffic, but we're going to have interactive communication among devices. And then the problem is, how do we, in the massive IoT, how do we get these devices connected to certain network with distributed ledgers and blockchains? And in the problem of ultra reliable low latency communication, the problem is, how do we define the latency with respect to the transactions, not with respect to a single transmission? So here we actually look at the latency of the consensus, not latency of single end-to-end transmission. So with that, I will actually round off because I believe my time is up. So we have to look into the interaction among different generic traffic types. We need to understand the changes that the IoT is going to suffer, is going to get from introducing smart contracts and transactions. Generalize probably the notions of timing and reliability. And machine learning is a must-have for guaranteeing and measuring ultra reliability, and nice to have for anything else. And spectrum allocation and usage needs to be redefined, going away from just spectrum efficiency towards how we support these different connectivity types. Thank you.
Thank you, Petar, for your interesting presentation on future 6G MTC scenarios.
Thank
you. Our next
sorry. Thank you.
Yes, you're welcome. Our next presentation is on Industry 5.0. Yes, you have heard it right. Industry 5.0 use cases towards 6G. It will be presented by Mr. Frank Burkhardt, who is the Group Manager for Industrial Communications at Fraunhofer Institute of Integrated Circuits, IIS, Germany. The floor is yours, Frank.
Hello. Now you should hear me. Thank you very much for the introduction. And well, as Nurul said, well, I will talk about Industry 4.0 use cases towards 6G. So the first question, of course, is in that case, well, if we're talking about that topic is what actually should be Industry 4.0, 5.0, sorry, I'm still somehow stuck in the old numbers. Well, so what shall this actually be? Because it's somehow, well, we have heard the numbers, but we don't have a clear picture about it. So if we take that, what we really know at the moment, well, it's a first revolution, second revolution, until the fourth revolution of industry. So that's quite clear. So we're coming from mechanization, we're going forward over automatization, and now we are here with cyber physical systems. So that's the point at the moment with the fourth revolution, but what's the fifth? So that's the big question. And if we have a look at also there with 6G, is wireless already enough to state something is Industry 5.0? Obviously, well, that cannot be, because if we have a look at industry at the moment, we see there is already a lot of wireless going on. So we can replace some mechanical connections, we can replace slide contacts, we have automated guided vehicles. We are already working with wireless for brownfield deployment. So it's not the point about just being wireless. So the question is then, what is it actually? I will try to draw it a little bit different. So here I've put in a figure showing where are we at the moment, and actually, so where do we want to go? So what is typically done at the moment is we are looking for applications that are wireless, which actually don't have a real-time requirement. So we don't care if, let's say, that information comes sooner or later, 1 second does not really make a difference. The only matter would be at some point that information is required. Or on the other hand, we have, I call them non-critical real-time applications where we have time. So real-time does not mean anything about how fast is it. It only means at a certain point in time, we have to have that information definitely. Not later, but to that point. And that point could be 1 hour later, for example. So this is the non-critical real-time. So from that, we're coming to the interesting point of mission critical real-time, and that is where really 6G comes into play and where also Industry 5.0 comes to play. So we are talking about very low latencies, and we are talking about a really, really hard requirements on reliability. So what my pre-speaker told, basically hard real-time. So this is how we can define it. So this is one topic that we have now, hard real-time wireless in the production, but does that already make it Industry 5.0? I would also again say no. We need something more. And what could that one thing more be? And my thesis here is we have intelligent productions. So at the moment, we are talking a lot about AI. We are talking a lot about intelligent products. Anything should be somehow intelligent. But the movement to a really intelligent production, that's something that's at the moment more a hatchling. So it's moving forward, but there will be years to come until that is fully deployed. And this is where we really can talk about, yes, that can be the thing that is Industry 5.0. So we're talking actually now about an industry which is highly adaptable, highly flexible, highly movable, and I would put it very, very simple. It is a production where man and machine can work together as a flexible team. So this is a first initial definition of Industry 5.0. I think, well, we can go forward to that as a base, with a base assumption, and we can update that, of course, by time and time if we discover that maybe there's something more to 5.0. So what will be the role of 6G then in that 5.0, assuming that my assumption is correct? In principle, it's a key enabler. First, obviously, we have the communication capabilities. And well, if we just have a look at the hard facts, we see we're really moving down to lower latency. We are moving down to high reliability. So this is, I would say, the basics that we need for that industry. But what's up in addition to that? And that is something that also my predecessor said. Basically, in my opinion, there's not a single wireless system that can fulfill all requirements, especially if you think about the famous triangle, that can fulfill all of them at the same time with good efficiency. So that's something I think that 6G will be the umbrella, taking all those specialized communication systems that are outside. They have the right to live there. So there's a reason why they are there, and really provide the umbrella for them. And then we can really have a fully capable communication system that can address, let's say, basically all the use cases in the best way. Then the next point, of course, is if we think about IoT or in general IoT devices, we see that there will be a huge growth of them in the next years. And 6G obviously the goal of 6G is to be very energy efficient, or in the best case, even to be zero energy. And if we want to have so many devices added, then we have to go that way, because else we will be building a lot of power plants, which I assume no one wants to have. And the last point I would like to address here is also that 6G addresses in its construction AI, so it's using AI for communication, but also it is, let's say, the backbone for distributed AI, so that we have not only, let's say, a distributed AI, but we can move, on the one hand, certain AI applications from one node to the next node, and by that we can achieve a reactive and really reliable cognitive production. So when we look now from, or we come from what 6G can do, what are basically really the use cases, what could be done with them in the industry? And here I've brought an idea from VDMA in Germany, where they put together what are the use cases that at the moment are addressed in the mechanical and plant engineering, and they want to address this already with 5G. And if we have a closer look at what is possible at the moment, we see, well, a lot of things are already possible, but there are gaps. The more we come to the right with the orange cases or orange blocks, we see there are many, many things that are at the moment, at least, not yet addressable. But if you're looking to the future, of course, well, there will be 6G at some point, and I see they will be addressable at that point in time. And if you have a look, what types of use cases are not yet, or applications are not yet fulfillable in a full way or complete way, then you see it's especially synchronization. You see field buses that are delivered wirelessly, and of course, very, very, let's say, close or detailed localization. So these are the things seen at the moment. But of course, as you see also on the downside, so there are new applications arising now on the horizon. And one of them would be, that I brought with me here, manufacturing as a service. So at the moment we have more or less, we have someone who has an idea, he wants to produce a product and then tries to sell the whole story. But what would be if we put it the other way around? So we have a customer with an idea and he just wants to have that product and he gets the means to produce it, just as a service. So he puts that, in that case we have here, he puts it to the cloud. Then we have distributed manufacturing. You can manufacture wherever you are in the world. And then with your supply networks, which are coordinated the best way, all that products or part products are brought together into a factory, which is not built for a single product, but is highly adaptable, which goes in the background of fluid production. And with that, we can assemble everything well, and then we deliver and the customer is happy. So this is something where we can go if we have a throughout connectivity, a throughout information management. And if we want to go to even, let's say, some more visionary goals or already mentioned visionary goals, well, then we have here on the one hand, definitely we have fluid production. So we have factories where, let's say, everything is mobile and all the production is revolving around the product. Then we have true collaboration. So with that, I mean, at the moment, let's say robots and human, they collaborate, but it's more or less something either the human does or the robot does. And to interact really with each other, there it needs to be really, you need AI, you need we need other sensors that are used, and with that you can really work interactively and intuitively. Next point would be, or next idea is teleport. So to really, if you have to do maintenance, and at the moment it's more or less, you have a telco, you try to somehow figure out what's happening, but if it's possible to really be there, or to have the imagination that you would be there at the point where something happened, and then you really can find out what's the reason. You don't have to go there anymore. You don't have to fly, you don't have to drive by car for hours, but you can really just be there and do the maintenance in the best possible way. That would be what I call teleport. Next, obviously, well, it's through the press, mind to matter. Why use a joystick? Why use a keyboard if you can just use your brain? That will take many, many years, but at some point we will be there. And then we control that just by thought. And that will again give a big shift to the true collaboration, because then you can, I would say, then you can talk to the robot, but not in your native language, but in the language of thought. And the final two use cases I brought with me are, or ideas I brought with me are zero cable factory and zero energy factory. The first one is obviously, why should we have any cables anymore in a factory? So if the connection wirelessly is good enough, then we don't need to cable for information. If we also provide the means to provide the energy, and there are already some ideas or experiments to do that, then also you do need cables for power. And that means we could go in that direction that at the end, there will be no cable at all in the factory. And obviously very far in the future, I hope earlier, not later, there's the idea of a zero energy factory. So that you have really a factory that does not need any external power supply at all, but brings everything it needs just for the production. I'm aware that these use cases are, well, they are far too reaching to the future, let's say, but well, in the end, we have to dream. And I hope that we can address that with 6G already, but maybe in some cases it could be that we are talking about the next generation. But I hope we manage with 6G. With that, thanks a lot. And back to you, Nurul.
Thank you, Frank, for the indeed interesting. It is indeed interesting to see the diverse set of futuristic use cases of wireless industrial networks for real-time applications. Let us now move from the 5th industrial revolution to the 6th generation wireless networks. It is our pleasure to invite Professor Ingrid Moerman from imec, University of Ghent, Belgium, to talk about holistic end-to-end 6G MTC network vision. Please, Ingrid.
Okay, so before presenting the vision, I would like to convince you about the need for a holistic end-to-end vision. And when watching past, present, and future evolution, we cannot ignore that end-to-end networking is characterized by diversity. So let me just illustrate you. And looking at the radio access level, we observe different spectral bands from sub 1 gigahertz up to millimeter wave bands. Each band has its own characteristics. Low bands are excellent for large coverage and dealing with mobility at the cost of larger latency, while high bands offer large capacity at the cost of more complex and energy-consuming technology and infrastructure. Traditionally, we observe two types of wireless access architecture, cellular versus local area. And in 5G, there is a trend for unification and multi-connectivity, actually treating cellular and local area networks the same way. In 6G, the notion of cell is actually completely disappearing. If we look here, starting from conventional cellular network, in 4G, the concept of coordinated multipoint is introduced, where multiple base stations in a coverage area cooperate to serve devices within the same area. In a further evolution, a device communicates with its closest base stations. And in the extreme case of cooperation, which is called cell-free massive MIMO, there is no notion anymore of cells, but we just have one big cell with distributed base stations covering the whole area. And we also have seen evolutions in network control architectures. In traditional networks, we have distributed embedded control on custom physical hardware. With software-defined networking, Network control is separated from the data plane, and the network controls happens by software based on a global view of the network. Next evolution is network function virtualization, where custom hardware is replaced by software functionality on commodity hardware, and a virtualization layer is added, and the network functionality is now offered as virtual software containers that share the same physical infrastructure. This requires a complex management and orchestration framework for deployment and control. The NFV architecture further allows to split functionality over different units, and it also allows shifting more real-time control functions closer to the edge. Also, traffic demands can be very diverse. This was already explained in the previous talk. So for most machine type application, low to moderate data rates are needed. And actually the latency is the most challenging one. So looking here, low latency does not necessarily goes together with high throughput. Only for the AR, VR, autonomous vehicular networks, both low latency and high throughput are needed. And subsequent evolutions are gradually reducing the latency by increasing the input. Another type of diversity is in the standardization landscape, as is illustrated here for 5G and NFV standardization. And a last thing I want to mention is 5G is seen as an accelerator for digital innovation in diverse industrial use cases. And we also observe several shifts leading to the involvement of more actors. We see a first shift from public mobile networks to more and many more local private networks. We always see that consumer-oriented basic connectivity services are migrating to more professional services with diverse quality of service needs. And besides the typical mobile network operator and equipment vendors, now we also have many other actors, smaller actors that come into play. And I would like to further illustrate the diversity with an example on time-sensitive networking. Today, we actually only have wired networks that can offer time-sensitive networking, and the de facto standard is TSN Ethernet, so an IEEE standard. In order to guarantee end-to-end bounded latency, all Ethernet devices need to be accurately synchronized with the master clock, and then the traffic can be precisely scheduled. In end-to-end connections involving wireless access, we need to support the same TSN features. And how can we do that? Which wireless technology is the most suited for extending wired Ethernet with wireless TSN features? We have two main candidates, which is Wi-Fi and 5G, each having their own standardization body. If we look at 5G, then the approach is to emulate the behavior of an Ethernet TSN switch over 5G infrastructure. And very recently, encouraging results have been shown with microsecond level timing offset. However, if we look at Wi-Fi, and this is where also at IMEC we are doing research. We are also looking to extend Wi-Fi with TSN features. And to do so, we use our open source Open Wi-Fi software-defined radio platform. And also with Wi-Fi, we can show that very low microsecond level synchronization accuracy can be achieved which is actually orders of magnitude better than what can be achieved today with state-of-the-art commercial chips, 802.11ax chips. So, without going into detail, both solutions, they have compatible performance and have their pros and their cons, as can be seen in the table. And 6G is not a matter of selecting one of these key technologies. It's a matter of using the one that is most suited in a specific situation. So we actually don't have an or story, but it is an and story. And this brings me to the holistic end-to-end vision. And end-to-end means that connectivity services are offered between the endpoints of an application that are running on end devices. And these connectivity services have to meet very strict traffic demands that are set by the application. The connectivity services can be offered by infrastructure, but can be also be offered by device-to-device communication, with or without mediation of infrastructure. The vision proposes a segment-based approach with cooperation between interoperable segments, rather than a unified and centralized approach as it is specified today in 5G. 5G is treating core transport network and multiple access network as one big integrated unified segment with complex control plane and complex standardization processes. Why not treating a core network as a separate segment that may interact with multiple access network using open standardized interfaces? This vision leaves more freedom to the segment in terms of mechanisms and in terms of the way they are implemented. Each segment could have its own specialized segment orchestrator, optimized for that specific domain, optimally leveraging domain expertise. Okay, looking a bit further, the data plane, of course, has to offer connectivity, and this can happen via multiple technologies, and it supports high precision communication, which means that it offers fine-grained end-to-end quality of service granularity that is customized for the application, but not restricted by technology-specific priorities or quality of service classes. The control plane manages the different segments and endpoints and goes together with a monitoring plane that has to offer measurability, meaning sufficient measurement points and advanced analytics that is needed for feedback on configurations and verification of end-to-end quality of service. And to allow this end-to-end verification, the control and monitoring plane needs to be extended also at the application level. And also we introduce a new plane, which we call the intelligent cooperation plane, that is responsible for the cooperation across the segments and for negotiation on end-to-end quality of service, end-to-end quality of service demands. And a key feature in this vision is the use of open, technology agnostic, vendor independent interfaces. So in the first place, between the application and the network. Second, between the different segment orchestrators. And third, also in the data plane as network service access points and the ingress and egress gateways between segments. Okay, and most important in this vision is the exposure of the right level of information across the segments via the open interfaces. So there is no need for collecting exhaustive information that is unnecessarily increasing the overhead in the signaling plane. Again, this leaves the freedom to the segments for fine-grained resource allocation or slicing in the segment, So each segment can follow its own granularity of slicing. So we are confident that such an end-to-end network architecture simplifies control and standardization and also allows easy upgrades and extensions, meaning that such an architecture is future-proof for further evolutions. And this concludes my presentation.
Thank you, Ingrid, for the intriguing vision on how to deal with diversity through a holistic end-to-end network architecture. At this point, I would like to kindly remind all our viewers that you may ask the question and answers at any time, so you do not have to wait for the presentations to end to ask questions. You can ask questions at any time through the Q&A window. As we all know, ultra-reliable and low latency communications is the most challenging of the 3 service classes in 5G. Undoubtedly, URLLC will continue to be a dominant service class in 6G era as well. Next, we would like to give the floor to Professor Christian Wietfeld from TU Dortmund University, Germany, to tell us about the future of URLLC in the 6G era. Please, Christian.
Thank you very much. I just need to share my screen. So I hope you can see the slides now. Thank you very much for the introduction. I would like to discuss a bit more in detail mission critical communications in the light of future 6G. When we take a look at the current state of the art, the latest 5G measurements of recently introduced features already in live networks available are impressive, and further future 3GPP releases will further improve the performance of 5G. Nevertheless, we cannot expect that these high-end solutions will be available everywhere anytime soon. When we take a more detailed look into the requirements of mission-critical machine-type communications, we will see that this reaches far beyond city centers, and such communication is needed in special environments, thinking, for instance, of rescue robotics, as well as self-driving cars. So in continuation of the previous talk, we believe that a broader multi-network, multi-technology approach is needed for future realization of these mission-critical machine-type communication services. In the white paper, we introduced some ideas on how to tackle these challenges. And the first idea is that we discussed the predictability of applications. Some of the machine-type communication applications are quite regular and have a uniform inter-arrival time distribution, and they can be realized quite cost efficiently. But the most challenging and costly issues are around the unknown inter-arrival time distributions, the rare events without any obvious predictability. And to address those, we have introduced in the white paper some solution components or potential solution components towards 6G. I cannot go into detail on all these technologies or proposals, but I would like to focus on 3 ideas that we have also addressed in our recent research. The first idea is that we do not want to treat all the networks with the same pre-planned scheme, but we want to learn from the actual real-life behavior of each of the networks to make opportunistic choices. This leads us to the idea of an AI-enabled resource awareness and scheduling. The second thought is that we do not want to trust a single public network, but we want to combine independently planned public networks and mix them with private networks as applicable and useful in order to instantly mitigate any upcoming issues. This leads us to the idea of a cross-network machine-type communication broker. And finally, we also do not want to trust the statistics and the learning from historical data only, but we want to run realistic models in parallel to the real-life execution to anticipate upcoming issues, and this leads to the idea of a real-time predictive network twin. Let's have a closer look at some results regarding these areas. First of all, some work on AI-enabled resource awareness and scheduling on the client side. In a two-step approach, we have first produced a data rate prediction based on passive indicators using random forests, which then in a subsequent step is used to make opportunistic choices using reinforcement learning to address the connectivity hotspots in a highly dynamic communication environment. And this has shown to be quite promising compared to a periodic scheme. We achieve with these adaptable machine learning enabled schemes higher data rates, lower battery consumption, and also these schemes can be applied not only for smartphones but also for tiny IoT devices using lightweight approaches. When we take a look on the network side, we have looked into a dynamic mixed critical network slicing approach. In this approach, we do not allocate resources in slices statically, but use AI or machine learning to learn about the characteristics of the different slices and then tailor the slices accordingly in order to not waste resources due to a static allocation of resources. And this has also shown some interesting results when we first take a look at the situation without slicing and looking at the scheduling latency and the capacity remaining for less critical services. We see that without slicing, we do not meet any scheduling latency targets. But with the static slicing, we can have very low scheduling latency, but we also reduce the capacity quite considerably. Once we combine the dynamic slicing with some machine learned experiences, we can achieve still some nice latency, at the same time increase the capacity. So these are some examples to use AI. One might wonder if this is more on the nice to have side or the essential part, but we were quite happy to achieve these results by using machine learning. Let's have a next look on how to manage different communication links. And there we have introduced the SCADES approach using, or as an example for a cross-network machine type communication broker. This approach can enable different types of networks and mix them accordingly to the needed performance. And we have applied this approach in various projects in the area of rescue robots, using or controlling ground robots as well as aerial robots, drones. And this has been done recently in several projects, for instance, in a, sorry, this was too fast. I go back one slide. Just a moment. So this is the, these are some results we have produced in various projects. For instance, investigation of the search and rescue drone in the Baltic Sea. Recently, we have introduced this 5G connectivity in the German Rescue Robotics Center. And during the COVID lockdown, we did some experiments by combining a public LTE network with some Wi-Fi deployment and have experienced very good results in producing reliable connectivity. The final idea is related to the real-time predictive digital network twins. This idea we are currently developing in the area of millimeter wave beam selection and steering. On one hand, we use a lab setup to investigate in detail the characteristics of millimeter wave and derive corresponding models for each of these links. And in a second step, we integrate this in a system level simulation, which in this case describes a logistics scenario with ground vehicles and aerial vehicles, which will be interconnected through millimeter wave. And this simulation is being realized by a lightweight ICT-centric mobility simulation, LimoSim, that we have introduced for both OMNET as well as NS3. So this brings me already to the conclusion of my contribution. We see that verticals requiring ultra reliable low latency communication move towards 5G technology, but yet in many cases various options for network design and operations are still to be considered. And with some results, I've shown some potential solution approaches to be applied to mission critical machine type communications towards 6G. Thank you very much for your attention and looking forward to the discussion.
Thank you, Christian, for the futuristic vision on mission critical MTC network. We will now move to the other end of the performance spectrum, from ultra reliable communication to zero energy MTC. With around 100 billion IoT connected devices by 2030, energy efficiency will be of utmost importance in designing a sustainable and green 6G MTC network. Our last presentation of the day is titled The Road to Zero Energy MTC by Mr. Ravikumar Pragada, who is a senior principal engineer at InterDigital USA. Please, Ravi.
Okay, thank you everyone for the wonderful presentations. I think the advantage of going last is you guys have already set the stage for me. It was nice to see a lot of talk about diverse set of use cases from everyone. And then Frank also talked about zero energy factory. Ingrid and Christian talked about need for low latency and URLLC. So with that, let me just get started here. If we look at the generations of technologies in the last 3 decades, my focus today will be mostly centered around cellular networks. So if you look at 2G starting, we're able to support millions of voice users, 3G with broadband era, and 4G where we're able to support billions of mobile users. As Nurul indicated, with 5G, towards the end of 5G, we anticipate to be able to support hundreds of billions of devices. But if you start to look beyond 5G and enter 6G era, we think there is anticipation that this number of devices might go up to 1 trillion, which we need to support. So today I'll talk about what are some of the challenges in scaling to these 1 trillion devices. If you look at the growth multipliers in terms of some of the key technologies in ICT, starting with even the downlink peak data rates that we see in wireless, there's at least been 6 orders of magnitude increase in data rates if we start with the GSM phase 1. And similarly, if you look at memory densities, memory capacities, CPU speed supported by Moore's law, there's been significant growth in terms of achievements here, orders of magnitude in the last 3 decades. This graph is on log scale, mind you. So if you look at the battery energy density, this has been really struggling. There's been less than 10x improvement so far. We believe one of the main reasons why IoT or IoE has not picked up and gotten mass proliferation, is always behind expectations so far, is mainly because of battery capacity. This is a problem that needs to be solved. So if in this world of 1 trillion devices, even if we assume 10-year battery life, which is very difficult to achieve with all the bells and whistles that we have in the 5G networks, 5G NR with the reduced cable devices that's just getting introduced, or if you look at all the advances that have happened in NB-IoT and MTC devices, it's very hard to achieve 10-year battery life. But even with that, you still have a whopping 274 million battery changes per day, which is simply not sustainable. And if you also look at sort of the use cases that others have presented so far, if you think of infrastructure inspections, you've got these sensors on the bridges to monitor bridges, oil and gas, flare stakes, wind turbines. Most of the practical use cases, it is not possible to go and change these batteries. First, there's a maintenance problem, and then sometimes these devices are hard to get to. So you can even think of, in construction, for example, sensors, moisture sensors that are behind the wall. So it's difficult to get to these devices, and the cost of swapping the battery or changing the battery is typically orders of magnitude more than the cost of the device itself, with the manual intervention that's required, the truck rollouts that are required, and so on. So there is a clear need to enable IoT device operations that are less reliant on the battery. And let's look at what's been done so far. Majority of the techniques, at least from a 3GPP-centric view, that have been adopted are discontinuous reception and power save mode. So DR, and both of these have some inherent trade-offs between device reachability and battery life. We've talked about the importance of latency, though from a URLLC perspective, from a connected mode, but even from an idle mode, there is a big challenge in terms of reachability or power save latency that's associated with these devices. If you have longer deactivation cycles, obviously they give you extended battery life, but at the cost of latency. Now, for those who are not familiar with power save mode, it simply means it's a deep sleep mode where the UE is negotiated with the network and it goes for hours or sometimes days together. It can go into deep sleep, but the challenge here is the device is simply not reachable by the network during these times. And depending on the kind of mobility that you're trying to implement in these devices for the use cases that make sense, there's also a bunch of measurement cycles that has to be there, and then the DRX will help you when the network is trying to page you. So here at the bottom, I wanted to show a simple figure. If you look at the device power consumption on the y-axis and time on the x-axis, of course, when you make uplink transmissions, that's where you're consuming a lot of power. And your power save mode, the deep sleep mode, is where you have the lowest energy consumption. And when you are doing measurements at DRX, there is a bit more higher energy consumption. And whenever there is a network event, there are other things that have to happen so that the UE can transmit. One thing that I would highlight is the terminology called transaction cycle. This is basically where you look at average time between two uplink transmissions is what is typically termed as a transaction cycle. And we'll come to that later. So I'll not go into details here, but I just wanted to paint a picture of what's been done so far in 3GPP, even in the more recent releases. So if you look at starting from release 13, let's say, with enhanced MTC devices and also similar for NB-IoT, they've introduced things like enhanced DRX, reduced control signaling, and then you get to further enhanced eMTC, and then even further enhanced eMTC. We're not good with names, but we keep on adding, further enhanced, even further enhanced, and so on. So there's introduction of wake-up signals, PDC-CH, the control channel is processed only if a wake-up signal is received, so on and so forth. Then you move to group wake-up signals, then a carrier-based DRX configurations that are starting to be looked at in release 17. This is the current release that's going on now. And in 5G NR, there's not been a lot of focus on IoT yet. I think release 17 is the first one that's starting to look at what is called NR reduced capability devices. But with all of these approaches, all of these tend to be very incremental, but more importantly, first of all, they suffer from this inherent trade-off that I talked about. The only way to save power is basically putting the device to sleep for a really long time. In other words, the device is not reachable. And second, all of them also use active components. And because these are active components, they tend to burn still some power and energy. And then you're not able to get the battery life will never be equal to the useful life of the device. And mind you, in most of these scenarios, the useful life of the devices are in terms of decades, going up to 3 or even 4 decades in some scenarios. So there's a clear need to find novel techniques that can handle and address these two aspects. So this is where the zero energy air interface sort of comes in. So first, let me define what we mean by zero energy air interface. We define it as an air interface that simply does not draw power from the IoT device's battery. And this is achieved. There are 3 main pillars I think of when I think of zero energy air interface. These are basically looking at controlled energy harvesting. This is RF-based far-field energy harvesting, on-demand receive, which sort of breaks this trade-offs that we talked about between latency and battery save. And then there's also need for enabling ultra-low power transceivers. So essentially, how do we get there? As I said, we need ultra-low power RF receivers capable of operating under 1 microwatt budget. We have a figure here. There's a reference that sort of shows if we surveyed the ultra-low power radios where we are. We are actually working with one of our research partners where we are able to enable ultra-low power receivers operating actually in tens of nanowatts and still be able to operate in urban macro sort of environments. And then the next thing that's required is enable zero energy radio operation. This is where you have simultaneous power and information delivery, thereby not relying on the batteries of the IoT devices. And overall, we also need a scalable framework that can support a diverse set of deployment scenarios, as the other presenters have presented, there's a lot of diverse scenarios when it comes to IoT. Okay, so first let's look at the zero energy receiver architecture. So the zero energy receiver is made up of all passive components. There are no active components here. The zero energy receiver operates by harvesting energy from the electromagnetic wave that's coming in. So it has two main parts to it. One is the ultra low power receiver part that is used to decode information that takes advantage of a MEMS device to give the required passive gain that it needs to operate in these macro environments. And then followed by ultra low power CMOS circuit, which basically helps us with the data decoding. And then there is the energy harvester, which is basically using an impedance transformer, also as a capacitor for storage, but then basically it's driven by a boost type converter. And the boost converter is basically the one that's powering the comparator and the bank of correlators to help with the data decode. So in terms of zero energy air interface operation, how does it look? Network transmits a power optimized preamble followed by higher layer data. This could be sort of your paging message, if you will, or could be a wake up signal, any of these sorts of things. And the device uses the passive receiver, the zero energy receiver, to harvest energy in band from the waveform and uses it basically to run the circuitry and process the signals that are received. The power optimized preamble may be constructed using an unmodulated RF carrier, or we could even think of multi-tone power optimized waveforms. The information sequence themselves, because we are focused on ultra low power transceivers, we want to look at very simple modulation techniques such as Manchester encoded on-off keying. And then overall, to make this truly zero energy, what we need is that the energy harvested from the power preamble should be greater than the energy that's required to decode the information in the body. So how do we start to bring this into a cellular framework? So here on the right, we look at an urban macro deployment scenario. UInterface, this is the name that's there today. This simply implies the interface between the base station and the device. For simplicity, I call it a type 1 device. This is the legacy device, if you will, the one without the zero energy, and then type 2 device is what we're introducing here. And we want to bring in a zero energy downlink as a supplementary air interface to the UU interface. So the main idea here is basically move as much of the idle mode functionality in the IoT device from the UU interface to the Z interface. So the Z interface is the passive component, doesn't need any energy at all. So if we are able to offload all of the idle mode in terms of measurements, in terms of wake-up signals, paging, all of that stuff, then you're able to significantly save power and put the main transceiver in have it in the deep sleep mode always. So that's essentially the idea. And in connected mode as well, there are scenarios where you could leverage Z downlink. Basically, these UU transceivers tend to, for IoT specifically, they tend to be half duplex. So when you're making uplink transmissions, you need to typically make multiple uplink transmissions to get the range. You could use the Z downlink to help with getting acknowledgements and so on, and terminate uplink transmissions early on. It's also possible where we can not only use the Z downlink for a zero energy air interface, but also we can use this to compensate for the battery leakage power that we have when the device is in deep sleep mode. So just very simply at a high level, some results to show what we've done and where we are. There's a lot of results I'll not be able to go through given the time, but just to give you a picture from what we have seen before with the zero energy now, when we make uplink transmissions, of course, you consume a lot of power, but in power save mode, the device is pretty much in deep sleep. Whenever the network needs to reach the device, it transmits a power preamble followed by a higher layer message on the zero energy air interface. And then the zero energy air interface can wake up the main transceiver and do its uplink transmissions. And the zero energy can also help, as I said, in terminating uplink transmissions earlier. So from what we have seen, this is the bottom curve is basically what is there from today's technology. This is using the PSM and DRX modes. And as you start to use the zero energy concepts that I just talked about, you are able to reach up to 3 or even up to 4 decades, depending on whether you're also enabling uplink early termination for these devices, depending on the transaction cycle. So for IoT devices that are that need to communicate much more frequently within a day, then there also you still see significant gains. But as you see use cases which have longer transaction cycles, then the gains are even more significant. And you don't have this tapering or DRX cycle limited region as you have in today's systems as you move for higher transaction cycles. So just to throw some applications enabled by zero energy technology, I think as you can see, with the zero energy technology, we are now able to increase the battery life of these devices by almost 3 decades. At the same time, break the trade-offs and be a device being able to reach by the network within subsequent latency. This is the idle mode of power save latency. And then with this, now you can think of a ton of verticals where it could help. So I'll not read through this, but as you can see, industrial IoT to infrastructure monitoring to asset monitoring and so on and so forth. And it also enables a host of new use cases that are not possible today by enabling what we call true wireless sensors. And when you think of wearables and batteryless implants, this sort of becomes really, really important and almost a game changer there. So to conclude, scaling to 1 trillion devices will require us to reimagine the radio transceiver, the air interface, and the overall system. As everyone mentioned, not all IoT verticals are created equal. We need to really find a way to break through this power save latency versus the battery life trade-offs. We need to develop ultra-low power receivers that consume few tens of nanowatts, and we truly believe this is within reach. We're almost there. We will demonstrate this in a year or so. On-demand features will have to be introduced into cellular frameworks by introducing this new class of zero energy air interfaces. And using this fine MAC concepts, we can enable a scalable system framework that can be integrated into future cellular networks. With that, thank you. Nurul, back to you.
Many thanks, Ravi, and also to the other panelists for your insightful presentations. It is now time for the question and answer sessions. As we have indicated, you may write your questions in the Q&A window, either using your full name or anonymously. We already have a good number of questions here, and in fact, some of them have been answered. So I will just go to the questions first. The first question is from Professor Dr. Selma Saidi, and it's directed at Petar. And the question is about machine learning. So how can we integrate machine learning with a lot of knowledge that we have from analytical modeling? So how do you build a bridge between these two systems?
Yeah, so first, I will come back to what I said before about nice to have and must have. It's a little bit provocative way to say something which is mathematically stated as necessary and sufficient. So what I'm saying is that there are cases where you simply must have machine learning. You cannot do it in any other way. And if we have the parameterized models, as it was asked in the question, then we need to sufficiently well learn the parameters of these models. And then if you, for example, want to guarantee a reliability of 10 to the minus 5, you cannot learn the parameter of your model with 5 samples, because then you cannot guarantee 10 to the minus 5. So that's the essential. This is basically mathematically provable about how many samples you need to have in order to claim some reliability. So on the other hand, and that's the problem of modeling. On the other hand, there are cases where we even do not have a good model. For example, if there is a long-term dependency, long tail, especially in some end-to-end applications which were mentioned before, which involves many modules, actually it's very difficult to model the composed latency of all of them, right? So we need to see how they're interacting with each other. And in that case, I would say machine learning is also essential if you cannot bring a model in order to calculate the probability that something is happening, right? Because we are very easily stating that it's 95%. Yeah, that's great, but with respect to what? This 95% is some distribution that nobody really knows. And these are the statistical grounds for having a need to use machine learning. And also, on the other hand, the cases where we have some complex algorithms, what, for example, Christian was showing was some resource allocation algorithms, where in principle we could use methods without machine learning, but they would not perform as well. They would not meet the guarantees. But even in that case, if with those algorithms you would like to guarantee the performance, you must use machine learning in order to, in practice, tell that the distribution behaves as you wish. So, I guess this is kind of answering the question.
Thank you very much, Petar. The next question is from Professor Gilberto Berardinelli. It's directed at Frank. And the question says, do you have examples of industrial applications that may require 100 microsecond cycles?
Yes. So in principle, it is, we have to be careful here with cycles and on the other hand, latencies, because what I showed in the presentation was basically latency. And the applications with that low latencies are mainly motion control. So we have to see, we are doing something, we require a reaction, which is a motion, and there we need that very, very low latency. And obviously, this is also a matter of a question of speed or motion speed. So the faster something is moving, the quicker the reaction or the smaller the latency needs to be. And to take also the other side, if we're really talking about cycle time, then that would mean we can take the current field buses, which are at the moment providing cycle times, meaning one message to the next message of 125 microseconds at the moment, for example, with Profinet, but they are also going below that already.
Yes, thank you very much. So next, again, we have the next question is again from Professor Salma, and it's directed at Ingrid. So basically, she's asking about defining open interfaces for the end-to-end network architecture, and she asks whether do we see this as a challenge because of the how the standardization process goes on now. So Ingrid, would you like to answer the question?
So it's about the standardization process. Yeah, I think the standardization today is great. A lot of work is done, and it's a great effort, but it also appears to be extremely complex. So that's why I was introducing this more open interfaces, which of course have to be standardized. Otherwise, you cannot interact between the different segments. And by focusing on the interfaces, you can actually leave a lot of freedom within the different network segments where the standardization bodies are doing a great job, or where you can even have more freedom to have even proprietary solutions, as long as your open interfaces are standardized and as long as you can exchange the relevant information. Also, from an end-to-end point of view, you do not have to exchange all the possible information to the highest level or to the central level to take a decision. Many decisions can be taken locally without exposing all the information. But coming back to standardization, the problem is the standardization landscape is quite distributed, and every standardization organization is doing its job. And maybe we have to go beyond that, and we need some kind of cross standardization body that can look beyond that, and that can look at more at interoperability across standards. That could be a way to go. Not sure if that answers the question or.
Yes, thanks, Ingrid. So the next question is also very related about the standards and standardization, and it's asked by Konstantin Mikhailov. Basically, he's saying that the current standard is, let's say, more or less driven by 3GPP. And how do the panelists consider to be a feasible roadmap towards having an open standard that is like accessible to the, let's say, wider community?
He doesn't. Or I think I already was partially addressing in my previous answer that indeed the 5G, the 3GPP is doing a great job in changing the whole ecosystem, but actually it is wider, and I think indeed also non-original, 3GPP technologies are getting involved. And that's why I think that we need to think also outside the traditional standardization bodies and see how to solve interoperability. Do we have to solve the interoperability within the standardization? Do we have to bring in Wi-Fi into 3GPP, or do we have to see something different, have some look at some different standardization that looks at interoperability between Wi-Fi or between IEEE and 3GPP. This is now getting a very complex system, which I also have shown in the presentation, like for time-sensitive networking, where now 5G is actually bridging between over the whole 5G core and access network to offer time-sensitive features the same like in Ethernet. Is this the way to go, or is it better to look something that is more interoperable and that can more easily connect not only to 3GPP, but also other wireless technologies? I think having a discussion about interoperability at a different level, at the, what I mentioned, the cooperation plane level, would be very helpful with a good link towards all the different standardization bodies. Because we should not come up with yet another. There are already so many standards, and we keep having more and more standards, which makes in the end the system very complex. So we should look at simplification.
Thanks.
I can add.
You know, I could just go ahead.
So I can just add briefly to this because I think it was to all panelists. The thing is that whenever we have different interfaces which we are treating as boxes, it's you can always achieve better if you open the boxes and optimize, the parameters by sharing more information between them, which is what I mentioned, the non-fashionable term of cross-layer optimization. In short, the latency, end-to-end reliability, and energy expenditures are system-level parameters. So it's very difficult to optimize them by having systems which are black boxes only with interfaces, because it's always good to open the system and design them from scratch for the full system. So we have to find the right trade-off between how much openness and scaling we allow, which is what Ingrid was presenting is actually a good architectural design, which allows scaling, proliferation, and so on. The point is that latency and energy are physical resources, which you can squeeze as much as you can from different blocks. And it's not possible to squeeze more if these blocks are not optimized for that purpose. It's like a difference between ASIC and a general purpose computing system.
Yeah, so Nurul, just to add to that, I think there are a lot of practical considerations to this. I mean, I do fully agree with Ingrid and what Peter are saying, but there are multiple challenges when it comes to real practical standards and what's happening in the industry, right? Even if you look at 3GPP alone, even though there are open interfaces that are not truly open, I think there is a lot of momentum in the industry now as we start to look at open RAN and open systems. For those following Open RAN, there's a lot of momentum now to really break down these interfaces, and that's happening. And I think that will continue more and more towards 6G. There is a lot of efforts already within 3GPP to integrate with Wi-Fi, right? Because these are two major standardization bodies that are out there. There is a lot of loose internetworking, tight interworking that's going on. It will continue to happen, but having this true vision of complete, the vision that Ingrid presented, I think It's very nice. We hope we get there, but it seems difficult from an industry perspective from where we are. I think there are multiple other challenges, logistical challenges that are out there and other forces in the industry that won't necessarily allow for this to happen. So we have to be practical also in terms of what's achievable.
Maybe if I can add one remark, basically I agree to the previous speakers, and from our experience building multi-network solutions, standards from the IETF come into play a lot, because IETF is traditionally used to work with different access technologies, although we don't want to diminish 5G as an access technology only, but in a way they are used to work with different standards, and potentially they can add some part of the solution.
I actually agree here. I think there are also a lot of efforts happening in IETF, and I think IETF is a fully open standardization organization where they can definitely also at the control plane level offer some more high harmonization or more interoperable ways to communicate between different network segments. And I think it's definitely, I should have added that to my slide on my standardization. The IETF is an important one. Also the way, the mechanism of IETF can be helpful also to promote end-to-end connectivity for machine type communication in 6G era.
Yes, thank you very much. I think that that was a very interesting question from Konstantin, and it triggered a lot of discussion. So we have one more question. Yes, and which I think also has already triggered a lot of discussion among the panelists. And this question is very interesting actually, because it's talking about cognitive radio, or in general dynamic spectrum management. The question says that previously there were a lot of studies about dynamic spectrum management, and do the panelists foresee this interest in this dynamic spectrum management arising again with these new concepts of in 6G era? So probably Christian, maybe you want to answer that.
Yes, I agree. Actually, the idea that I've presented on dynamic network slices, which use adaptable spectrum allocation, kind of resonates on this use of dynamic spectrum allocation. So it can be part of a complete solution to realize such requirements.
Yes, thanks. Ingrid, you wanted to add something to this?
Well, I think in the end, dynamic spectrum allocation is the way to go. Spectrum, of course, we are extending to higher frequency bands for having almost always larger data rates. But remember that in many situations, also dynamic situations, I mean, in terms of mobility or scenario or setting or whatsoever, the sub-6, or now we should say the sub-7 gigahertz bands will always be very popular for many scenarios, and in particular in machine type communication where you have very harsh environments. And exclusive spectrum allocation, as it is still happening today, I think it's not a sustainable model. A lot of spectrum is wasted because you always have the maximum amount of spectrum and you only use it when you need it. If you don't need it, spectrum is gone. So I think the only way to go is dynamic spectrum sharing. There exist a lot of mechanisms, but I think there is still the spirit is still there. If you don't own the spectrum, you cannot control it. You hear that in many situations. Oh, Wi-Fi cannot be reliable, unlicensed cannot be reliable because it's shared. I think there are many reliable solutions in Wi-Fi because Wi-Fi is local, and if you look at deployments apart from the big mobile operator networks, many deployments are very local, are on sites where even unlicensed spectrum behaves like licensed. So there is room, and there is, I think, dynamic spectrum sharing in future will be a must. There exist mechanisms. I would also like to refer to the DARPA Spectrum Collaboration Challenge, which was a 3 years competition where we participated and ended about 1 year ago, where we have shown that you can gain by sharing spectrum amongst different networks. So if you have exclusive spectrum, if you merge that spectrum, break the borders and share it, the spectrum efficiency is much higher and much more services can be supported. Of course, before it will be taken up, you also have to consider regulatory aspects to ensure that spectrum usage is fair enough, how to measure that, what is fairness, what if spectrum is violated. So I think there are still issues to be solved, but it should go in that direction and it should be dynamic, no static allocation.
Thanks. Petar, do you want to add something to this as well?
Yeah, just to follow up, I would say that we can also go to the exercise to say, with everything we know about the technology today, and we have the opportunity to define the spectrum usage from scratch, how would we do it? I'm not sure we're going to divide it into the blocks of frequency allocated separately to different services. And but I think it's still good to think about this, not only because it's intellectually appealing, but because there will be more and more spectrum that will be used by a larger number of devices. So we have to rethink the way of sharing, and which will go into the dynamic direction. That's one thing. And the second is what I also mentioned in my talk, is how we assess the spectrum usage when they're heterogeneous environments. I mean, heterogeneous requirements. For example, we have intermittent device which is sharing the spectrum with some link that wants a very high rate. How do we assess the efficiency of this spectrum? Because we have to take into account the uncertainty of the activation, how often it gets activated versus what is the usage of the spectrum because let's not forget that the Shannon formula logarithm 1 plus SNR assumes infinitely long transmissions. We do not have them in practice, right? So we have to basically reassess with respect to the real requirements of the users.
Yes, thank you very much. I think that also triggered a lot of interesting discussion, and I think it has been an open topic for quite long. We are running a bit short of time, but we have one last question from Professor Nandana, and it's directed at Ravikumar. So can you please elaborate on zero energy scenarios?
Thank you. I think it's a very broad question. So as I articulated in the talk, sorry, I had to rush through a bit, but there is a clear need for zero energy requirements, right? I think this was mentioned by Frank as he looked at Industry 5.0, but even closer term, even without having to move to Industry 5.0, I think there is a lot of use cases that really practical use cases that devices that need the zero energy, meaning you can't really go and change battery for these devices. The cost of changing the devices are even for many critical areas, especially as it comes to industrial IoT, trying to understand when to change the device battery is a huge challenge, right? This by itself consumes a lot of manpower to understand and keep track of when to change batteries for these devices, and having maintenance staff go there and remove and swap those batteries for, I mean, there were a few example studies that were already done. So if you have, depending on the kind of industry that you have, anywhere between 30 to 50,000 sensors on board, the amount of time and energy that it takes to maintain such a system, to make sure because these tend to be mission critical sensors, to make sure that the battery is not out is a big challenge. And that's where I think the zero energy technology comes in, where you sort of deploy them and sort of forget about them and not have to worry about having to go and monitor the battery status, change the batteries in this. We've talked about enabling this by leveraging passive components. The key part of the zero energy receiver is really leveraging passive components. And one of the key components of that is this MEMS device, right? So we are able to achieve a significant amount of passive gain, and these are significantly these are very, very cheap, right? These are cents on the dollar or sometimes even cheaper. And the MEMS technology has come a really, really long way. We are working closely with one of our research partners who've been working, who established themselves in terms of the MEMS and NEMS. And so I think there is an excellent opportunity for us to, one of the key things that I think when we look at 6G, or look towards 6G, many people, when they think of 6G, it's okay, let's increase the data rates, let's reduce the latency. Yes, those are true, those get attention, but the real challenges are being able to leverage advances that are happening in materials, advances that are happening in MEMS and antenna technology. You need to bring all of these aspects, disparate technologies, we need to bring them to really enable a true 6G MTC world. And I think that's where the zero energy sort of fits in. So I'll stop there, sorry.
Thank you very much, Ravi. We still have a few questions, but in the interest of time, we are already like close to 10 minutes over time. So we have to stop the Q&A session here. So I would like to thank once again all the panelists and all our attendees, viewers for attending this webinar. For your information, registration is already open for the next two sessions of the 6G Research Visions webinar series. The next one is next Wednesday on 18th November. It's about localization. And the following one is on the 2nd of December, and it's about validation and trials. Okay, please also fill in the online feedback form, which we will email to you after the webinar. And please use these hashtags and promote this, our 6G white papers and the webinars in social media. And please stay tuned to 6gchannel.com for further updates. Okay. Thank you once again, everyone, for attending this webinar. It has been our pleasure to host you today. Thank you.
Thank you, Nurul. Pleasure to be here.
Thank you.
Thank you very much.